Hi everyone and welcome to the Learning Curve. In this lesson, I will be illustrating how to carry out hypothesis testing for single proportions. This is a continuation of my series on hypothesis testing. I've previously released lessons on hypothesis testing for single means. This is my first in illustrations of hypothesis testing for proportions. Here we are told that the records of a state-owned company indicates that of all vehicles undergoing emissions testing during the previous year, 80% passed on the first try. We are told further that a random sample of 200 cars tested in the country during the current year reveals that 72% passed the initial test. Does this suggest that the true proportion for this country is less than the previous countrywide proportion? We are asked to test this hypothesis at the 5% level of significance, that is at alpha equal 0.05 or 5%. Generally, we use hypothesis testing for single proportions when we want to test to see if there has been any change to an established claim or an established percentage relating to the population or a population from which a sample has been drawn. In this particular case, the established percentage that is being challenged is that the emissions testing during the previous year suggested that 80% of vehicles passed on first try. So that 80% relates to the population of vehicles, and that is the figure that is being challenged in this particular question. This is typical to a hypothesis testing for single proportions, where there's a percentage or proportion related to a population that is being challenged using a sample that is drawn, a contemporary sample that is drawn from that population to see if there is enough evidence from the sample to suggest that the population percentage may have decreased or increased or has changed in one of the two directions, which is the case for two-tailed tests. So let's start. We are asked to state firstly the null and alternate hypotheses to be tested. So the null hypothesis, we use the symbol H0 for the null hypothesis, and we use the symbol H1 or HA for the alternate hypothesis. Now the null hypothesis will reflect the established condition or the established percentage regarding the population that is being challenged. And so the null hypothesis here would be that P, the population proportion, P is the symbol for the population proportion, is equal to that 80%, which is the old or established percentage that is being challenged in this question. So the null hypothesis here would be that P, the population proportion, is equal to 80% or 0.0 or 0.80. The alternate hypothesis now would reflect the challenge that is being put forward to the null hypothesis. At all times, the alternate hypothesis reflects a contradiction or the challenge that is being proposed. The change or challenge that is being proposed to the null hypothesis. Recall again that the null hypothesis reflects the established claim or condition that is being challenged, which in this case is that 80% of the cars, vehicles, pass the emissions testing on first attempt. Here in this question, we're asked to determine if the data suggests that the true population of this country, population of vehicles in this country, is less than true population of cars in this country that has passed the emissions test is less than the previous countrywide proportion. So this will be a one-tailed test. So the alternate hypothesis reflects exactly what we are testing. We're testing to see if the proportion or percentage of cars in this country that has passed the emissions test is now less than here, less than the previous countrywide proportion of 0.80. So the alternate hypothesis here would be P, the population proportion, less than 0.80. Both values in the null and alternate hypothesis will be the same. What will be different is the signage. The null hypothesis will generally always have an equal sign, while the alternate hypothesis will either have less than, greater than, or not equal to, depending on the specific scenario in the question. So here we have established a null and alternate hypothesis. Now we're asked to state the test statistic. So using the principles of normal distribution, the test statistic for a hypothesis test of proportions will be that Z is equal to P hat, which is the sample proportion, minus P, which is the population proportion, divided by the square root of PQ over N. So that's P hat minus P divided by the square root of PQ over N. We're not going to do any calculations at this stage. At this stage, we are simply stating the formula that will be used to derive the test statistic or calculated value. Now we're asked to show the region, the critical region, graphically. To show the critical region graphically, we're going to draw the standard normal distribution curve. And this curve is going to be very important to making a decision as to whether we will either go with the null hypothesis or support the alternate hypothesis that has been proposed. So we draw the standard normal curve, which is a curve that is symmetric around a center value of 0. Think of this as a number line. So we draw the normal curve, and because this is a one-tail test, we will be shading a value in the left tail of the curve. It's a left tail test specifically, rather, so we'll be shading the left tail. We'll be shading critical or rejection region in the left tail. Because the alternate hypothesis says less than, we will shade in the left tail. If it was greater than, we would shade in the right tail. And if it's not equal to, which is a two-tail test, we would shade a critical region in both tails. So again, in this particular test of proportions, we will be shading the critical region, the area to the left of the critical region, in the left tail. So the critical region, the critical value itself, which we will now determine, will be marked in the left tail of this standard normal curve, and the area to the left of it will be shaded because this is a left tail test dictated by the fact that the alternate hypothesis says P less than 0.80 or less than, which is the most important thing there. So to determine the critical value will help us to determine the rejection region, to separate the rejection region from the non-rejection region. That's the purpose of the critical value. We refer back to the question and we realize that alpha, which is the level of significance of the test given to us, is 0.05. So I'll write here alpha, the level of significance, is 0.05 or 5%. Because this is a one-tail test, I do not need to divide alpha by 2. If it was a two-tail test, meaning that the alternate hypothesis said not equal to, which would be dictated by the specific circumstances of the question. If it was a two-tail test, we would divide by 2. But since it's a one-tail test, whether right or left, in this case it's a left-tail test, whether it's a right-tail or left-tail test, you do not need to divide alpha by 2 when you're trying to come up with the critical value. So we're going to subtract 5% from 100%. If it's a one-tail test, just go right ahead at this stage and subtract the alpha value from 100%. If it was a two-tail test, you would divide alpha by 2 and then subtract that value from 100%. But this is a one-tail test because the alternate hypothesis simply says P less than, so we are left tail. This is a left tail test. So 100% minus 5% will give us here 95%, or as a decimal, that will be 0.95. So what we're going to do now, having found this probability figure of 0.95, is that we're going to go into the body of the normal distribution curve and look for a probability of 0.95, or the closest thing to it, in order to read the critical or Z value that corresponds to 0.95. So we go to the standard normal curve and we're looking in the body of the standard normal curve for 0.95, or the closest thing to 0.95, and it's right here. We see 0.945, and we also see 0.9505. Both of these are equidistant. They are of equal distance from 0.95, so we can use either of them, and it's fine. So I'm going to use 0.505 because that is one of the closest numbers here, the other being this, to 0.95 itself. You could use the critical reading for either of them. So now to determine the critical value corresponding to 0.95 here, I look at the Z column coming down here, 1.6, and then I look at the Z value going up from 0.95. The Z value going up from 0.95 is 0.05. So that means Z critical reading is 1.65, which is just an addition of 0.05 and 1.6. So that gives us 1.65, which is the critical reading or table reading that corresponds to the probability that we're interested in, which is 0.95. So therefore, I will write here, therefore, Z critical, or Z alpha, is equal to 1.65. So that means now I will go into the left tail of the curve, and since this is a sketch, it really doesn't matter where in the left tail we go, right? So I'm going to go into the left tail of the curve, and I'm going to locate I'm going to locate negative 1.65, because this is a left tail test, although the reading that we got is a positive 1.65. Because it's a left tail test, you're going to use negative 1.65. And again, it's a left tail test because the alternate hypothesis has a less than sign. So we locate negative 1.65 in the left tail of the curve, and you're going to always shade in these situations the area to the left of the critical value. So 1.65 is our critical value here, and this shaded region to the left of negative 1.65 is our critical value. So that's my critical value. So that's our critical value, or critical region or rejection region. We can use either. So the shaded area there to the left of the critical value, again we're going left because this is a left tail test. This would be the rejection region, or we could have written critical region as I was indicating before. So this is my rejection region. It means that any value, any calculated or test statistic value that falls to the left of negative 1.65 will lead to us rejecting the null hypothesis. So this is our rejection region. The purpose of the critical value of negative 1.65 is to separate the rejection region, entire area to the left of it, from the non-rejection region, which is the rest of the curve. So the rest of the curve is our non-rejection region. Non-rejection region. Okay? So now we have set up the test very nicely to allow us to make a determination as to whether to reject or not to reject the null hypothesis, which is the whole point of a hypothesis test, to either reject or not to reject the null hypothesis based on how the test statistic or calculated value compares to the critical value. So, in the next step, where in part D of the question, we're asked to evaluate the test statistic. And at this stage, we're basically going to rewrite the test statistic formula. So we're going to say Z equal P hat minus P divided by the square root of PQ over N. And this is where we're actually going to carry out our calculation of the test statistic. Now let's go back to the question. P hat is the population proportion. This 80% here relates to the population, and that's the figure that is being challenged. So P hat is going to be the sample proportion. So we know what P is. P is the population proportion, which is 0.8. Now we need to determine P hat. P hat is the sample proportion. This is what I call P hat. P hat is the sample proportion. P is the population proportion. So let's determine these. P hat is the proportion from the sample. It says a random sample of 200 cars tested in the country this year reveals that 72% passed the initial test. So P hat, which is the percentage derived from the sample, would be 72% passing the test. So P hat is therefore 0.72. But P is the population proportion which is being challenged, which is the 0.80. And that's the population proportion. We're going to divide that by the square root of P, which again, P is 0.80. And P plus Q must add to 1. So because P is equal to 0.80, then it stands to reason that because P plus Q, which is total probability, must add to 1, then Q is 1 minus P, which is 1 minus 0.8, and that gives us 0.2. So Q is 0.2. So this is 0.8 multiplied by 0.2 divided by N. N is the sample size or number of observations used in the sample. The number of observations used in the sample to establish some evidence to see if there is enough evidence to challenge the null hypothesis or the population proportion. The sample size that was used is 200 cars, so that's N, the sample size. So we're dividing by 200, and now we're going to simplify this. So to simplify this, we take 0.72. So our first step, we're going to take 0.72 minus 0.8. And that's going to give us negative 0.08. We're working on our test statistic value here. And then for the denominator, we're going to take 0.8 multiplied by 0.2 divided by 200, and then we're going to take the square root of that figure. So it's the square root of the entire thing. So 0.8 multiplied by 0.2, then divide by 200, and then we take the square root of that answer, which is 0.008. The square root of 0.008 gives us 0.028, rounded to 3 decimal places. So the denominator here is going to be 0.028 rounded to 3 decimal places. Now, again, how we arrived at that 0.028 is to multiply 0.8 by 0.2, then divide by 200, and then take the square root. Or you can, of course, just insert everything under your square roots in the calculator. Now our next task is really our final task here with the test statistic is simply to divide negative 0.08 by 0.028. And when you do that, you get negative 2.86 rounded to two decimal places. We're rounding to two decimal places here because we're going to compare it to the critical value, which is also rounded to two decimal places. So what we need to now do, so we have come up with the critical value or test statistic value, which is negative 2.86, and then that will help us to answer the final question. Do we reject or do we fail to reject the null hypothesis and state our conclusion? The thing that we need to do now is to check the critical value against this test statistic value. Or, put another way, to check to see where this test statistic value of negative 2.86 falls in relation to the critical value of negative 1.65. Does it fall to the left of it in the rejection region or to the right of it in the non-rejection region? That's what we need to determine here. So remember now the center value here is 0. So as we move leftwards, the values are decreasing. So thinking of this as a number line, we move from 0 to negative 1 to negative 2 to negative 3 and so on. So negative 2 would clearly fall, negative 2.86 is clearly going to fall to the left of negative 1.65. So what we realize here, therefore, is that negative 2.86 falls in the rejection region. So negative 2.86 falls in the rejection region. So because negative 2.86, which is our calculated value, falls in the rejection region, we must now reject the null hypothesis. So our conclusion is going to be we reject the null hypothesis. And our reason for rejecting the null hypothesis is because the test statistic falls in the rejection region. The test statistic falls in the rejection region. The test statistic falls in the rejection region. Or we could look at it another way and say the absolute value of the test statistic is greater than the absolute value of the critical value. Absolute value is the positives. The positive of any number is its absolute value. So that's another way to look at it. When that happens, we reject the null hypothesis. If we had gotten a result from this test statistic, like say negative 0.5, then that would fall in the non-rejection region here, and we would conclude that we failed to reject the null hypothesis in such a situation. So we reject the null hypothesis because the test statistic falls in the rejection region, and support because we're rejecting the null hypothesis. It means that by default we are supporting the alternative hypothesis. This suggests that there is enough evidence that the number of cars or vehicles, the number of vehicles passing the emissions test on first try have decreased. On first try have decreased. Which is what the alternative hypothesis is really saying. That the percentage of cars passing their emissions test on first try is now less than 80%. And so what we did is that we tested the hypothesis to see if the results from the sample drawn from the population of vehicles suggest that there has been a change in the population proportion of vehicles passing the emissions test on first attempt. What this test has shown us, by virtue of the test statistic value falling in the rejection region, is that the evidence is sufficient to reject the null hypothesis that the population proportion of vehicles passing the emissions test on first attempt is 80%, and instead support the alternative, which, which indicates that there may be enough evidence, or rather there is enough evidence to suggest that the proportion of cars passing the emissions test on first attempt has now decreased from what obtained before. And these are the fundamental principles that govern hypothesis testing for single proportions. I will be doing a follow-up video with more illustrations on this topic. Thank you very much, and I hope you found this video to be extremely useful and provocative intellectually. Remember to like, subscribe, and stay tuned to the learning curve for much more content. Thank you.